Hello, my name is Young Park, a PhD student of DGIST in Korea working with Professor Sang-Yun Han. Today, I will talk about fully reconfigurable coupled-resonator optical waveguides with 10 nanowatt static power MEMS. Ring resonator is an essential component for many photonic integrated circuits. One of the main functions of ring resonator is filtering. Cross consists of several ring resonators. By having multiple rings coupled together, one can have high-order filtering response. This graph shows a good example of cross usage used for filtering. As the number of coupled rings increases, the spectral response gets flatter. But when we fabricate cross, we cannot make it perfect as we designed it because both resonance wavelengths and couplings are highly sensitive to fabrication error. Therefore, active tuning mechanisms are needed for post-correcting the errors. In addition, it is desirable to program the filter's response to adapt users' need. For this purpose, thermal tuning has been widely used. But thermal tuning consumes high power as large as 10 mW per element. So, it is very difficult to scale up using thermal tuning methods. Another tuning method, MEMS, is also applied to tuning resonance and coupling. One of the great benefits of using MEMS is dramatic power reduction. However, no full reconfigurability has been demonstrated yet. So our work demonstrates fully reconfigurable cross with low power based on electrostatic MEMS. What we mean by full reconfigurability is tuning all the couplings and resonances simultaneously but independently. This is our device configuration. The device has two rings and two bus waveguides. There is a tunable coupler between our rings and waveguides which can control the coupling ratios. There are also tunable phase shifters next to every ring. The tuning is enabled by electrostatic MEMS actuator which consumes dramatically low. The left figure shows the SEM image of the MEMS tunable coupler implemented in our CLEO. The right top figure shows the operating mechanism. There are two waveguides located in parallel and one of the waveguides can be moved vertically by a MEMS actuator attached to it. The right bottom figure shows the simulated optical response of the MEMS tunable coupler with various vertical offset of the Moore waveguides. As shown in the graph, full coupling tuning from 0% to 100% can be achieved by moving the waveguide 1 micron only. For this design, we have about 200 micron long waveguides and the width of the waveguide is 450 nanometer. This slide shows details for the MEMS phase shifter. The working principle is pretty much similar to the tunable coupler in the previous slide. The difference is that now we have one main waveguide for waveguiding and the other waveguide for mode perturbation. The waveguide for mode perturbation is smaller than the main waveguide to prevent leakage. The right bottom figure shows the simulated effective index profile of the optical mode guided in the main waveguide. By changing the vertical offset of the smaller waveguide to change the distance to the main waveguide, the amount of mode perturbation changes and therefore the effective index as well. For this device, we have 1.9 mm long phase shifter to have full FSR tuning. The length required for full FSR tuning has exponential dependence on the minimum lateral gap, which is defined lithographically. We are working on more advanced design to reduce the length less than 100 micron. The left figure here shows the electrostatic cantilever actuator designed by our PI previously for large-scale MEMS switch. We used similar design for our CLEO device. The actuator is moved by electrostatic force between substrate and cantilever. The video of the right shows the MEMS actuator in our CLEO device moving up and down while the bias voltage applied to the actuator changes. The location of the cantilever can be precisely controlled by the applied voltage. From here on, I will show you some major data. In this slide, a single link coupled to a bus waveguide is shown. Device configuration map is shown in the middle. The rightmost figure shows major spectral responses with different voltage applied to the tunable coupler between the bus waveguide and the ring. As shown in the graph, the coupling strength is successfully varied with different bias voltage. This slide shows measured phase shifting. The leftmost figures show the configuration. By applying voltage to the MEMS phase shifter attached to one ring, we could shift the resonance peak as shown in the figure in the middle. Full FSR tuning is achieved with 12 volts as shown in the rightmost graph. By the way, the FSR of our device is about 12 GHz. Here, we show ultra filter configuration having two rings. By appropriately control couplings between the rings and bus waveguide and tuning the phase shifter, we could achieve flat top filtering response as shown in the graph on the right. This slide shows major dynamic response to MEMS tunable coupler. The coupler can be turned on and off within few microseconds. The right graph shows the measured current while tuning on the actuator. From this graph, we found the RC time of the device is 0.5 microseconds. This means that the actuation speed is limited by a mechanical response. So, we should be able to reduce the response time with optimized mechanical design. From the measured current graph, we calculated power and energy consumed by the actuator. To holding the position of the actuator, we only need 6 nanowatt. For reconfiguring the actuator, we only need to use 300 femtojoule. For your information, thermal tuning usually requires tens of milliwatt. In conclusion, we have experimentally demonstrated a fully reconfigurable cross having 2 ring and 2 bus waveguides. Each tuning element only consumes 6 nanowatt per static situation, and reconfiguration only needs 300 femtojoule of energy. Reconfiguring speed is also as fast as few microseconds. We are working on expanding this device to build a low-power programmable photonic array having large scale and low power consumption. This work has been done by collaboration with Prof. Kyung-Sik Yu at KAIST and Prof. Kwek and EFL. This work is supported by Samsung Science and Technology Foundation, KIT Center for Quantum Information, and NRF of Korea. Thank you for listening.